We have a wonderful program coming up. I'm David Eisenbud. I'm very pleased to welcome you to this Mathematical Horizons 1. Two wonderful speakers, and I'm looking forward to their talk. First is Saurav Chatterjee. He was a student of Percy Diaconis at Stanford. Then I'm happy to say he came to Berkeley. Unfortunately, he left Berkeley again after a while and went to New York and then came back to Stanford. But at least he's our near neighbor and a frequent collaborator and visitor here. He won the Rollo Davidson Prize in 2010 and most recently the Levy Prize in Probability in 2013. And I'm looking forward to his talk on nonlinear large deviations. Saurav.
Thank you for the gracious introduction, and thank the organizers for the invitation. So this is something that I have been working on for the last few years. I was asked to prepare the talk at the level of incoming graduate students, so that's what I did. I don't see that many incoming graduate students here. To all the senior people, please don't feel insulted if it's too easy, so I'll try to.
Well, we know just as little as they do.
Okay, so let me start by saying a few things about the area of large deviations. It's a technical part of probability theory. And there are two main goals of large deviations theory. One is to study the probabilities of rare events. So events that are very rare, the probabilities are very tiny, but you want to understand how tiny it is. And you want to understand the conditional distributions given that some rare event has occurred. So the thing is, the world doesn't look the same if something unlikely has happened. So things change. So you want to understand how things change, given that something unlikely has happened. So, a silly example here. What is the chance that you'll win the lottery? And the second thing is, how is your life going to change if you win the lottery? So that's the conditional distribution part. So often the second question is more interesting than the first, because the first is just a number. It's some small number, it's a number. The second question is more complicated. You don't know how things are going to be affected if something very unlikely happens. But it's usually essential to answer the first question before you want to, you can understand the second. So you have to know the probability of the event before understanding, and there are technical reasons for that, why that is necessary. So a simple example, the lottery example is some real life thing which is too complicated to capture by mathematical models. But a simple example is toss a fair coin n times, where n is some large number. And under normal circumstances, this is what you'd expect. You'd expect to get approximately n over 2 heads, okay, since it's a fair coin. And you also want to know the number of times you'd get 2 consecutive heads, so head and head, So roughly n over 4 pairs of these you'll get consecutive heads. Okay, so that's some simple probabilistic computation that you can do. So suppose the following rare event occurs, that instead of n over 2 heads, you get 2n over 3. Okay, so if you're tossing the coin 1,000 times, instead of getting 500 heads, you get 666 or more heads. And there are some general purpose tools. I'm going to briefly describe how these computations are done. So for this event, you can write down the probabilities approximately asymptotically. It's like e to the minus n times some number. Okay. Moreover, you can make conclusions like the following, that if this happens, then this thing, the number of consecutive heads, pairs of consecutive heads that you get, instead of being n over 4, it will likely be 4n over 9. So it will increase. So you can say this kind of conditional thing, that given this rare event has happened, you see other things also changing. Other things that were very likely before become unlikely now, and things that were unlikely before become likely now. So this is a very simple thing. You can do it in many ways. If you're familiar with Stirling's formula and all that, there are 100 different ways you can do this. But as in math, there is only one way which generalizes. Okay, so there are many ways to do this, but there is only one way which becomes abstract and generalizes to a more complicated settings. So the next slide will be a little bit of math. And then I'll move back to this mode where I'm not showing. So just this one slide of math I have. So this is how you do this. So how is this estimate obtained, this probabilistic estimate that I wrote down? So this is how you do it. It's a little bit of an undergraduate exercise. So suppose x1 to xn are independent random variables. Each is 0 or 1 with probability to half. Then the number of heads in n tosses is same as the sum of these random variables. And then you do this little computation here. So you want to find the chance that you get at least 2n over 3 heads. So you take some theta. You write this event as saying e to the theta Sn is bigger than e to the 2 theta n over 3. So these two are the same things. Now this is this general purpose Markov inequality that you have in probability, that probability x bigger than t is less than expected value of x over t. So you just write this down. Now, the nice thing about this one is that it's a product of independent random variables, so it breaks up as a product of expectations, and each of them is easy to compute. These are just 0, 1 variables, so you can write this down. So you use Markov's inequality, use independence, and then you optimize this bound over theta, and you get some upper bound on this probability. Okay, so this is less than or equal to. Now, the interesting thing is that this upper bound is actually the correct asymptotic, and that requires a different idea. Now, both this technique and this other idea, which I'm not showing here, they generalize to an abstract setting, and this is sort of the beginning idea in the theory of large deviations. This is how you compute large deviation probabilities in most cases. So you see, there are several things here. They're independent random objects. They're summing up to give something, and then you apply this Markov inequality, and the key point is that this expectation breaks up as a product, and then you optimize, and you get a bound, and it's unclear why this bound should give you the right answer, but it does. And so this example has this built-in linearity, which allows you to compute this expectation, and this idea generalizes. There's a fast generalization of this simple idea and the corresponding idea for the lower bound, and this is the main technique behind the theory of a classical theory of large deviations. So you go from the 0, 1 random variables to more complicated objects. You go to function spaces and you generalize, and you get amazing things. Literature spanning 50 years. But the thing is, there are no general tools for nonlinear functionals. Okay, so there is this linearity here. Okay, but there are no tools for nonlinear functionals. I'll give you an example in the next slide. Okay, what I mean by nonlinear. And so you see, you understand how linearity helps in the previous slide. In this expectation breaking up as a product, because you get a sum of independent things, or in linear combination you can do the same thing, but with nonlinear you cannot do the same trick. Okay, so here is a real life example, So analysis of real world networks. So this is becoming more important these days, and lots and lots of papers. Now, the thing is, rare events on networks, large deviations on networks, are often nonlinear in nature. Okay, so consider the following simple model. There are n individuals, and any two are friends with a certain probability p and not friends with probability 1 minus p, and friendships are all independent. Okay, so this is known as the Eder-Shreni model, and this is not realistic, mainly because this assumption that friendships are independent, which is not true in reality, but this is the first step to understanding real networks. Okay, so in graph theoretic terminology, an individual is called a vertex, and a friendship is called, it's called an edge. There's a model of a graph, and you have these edges in the graph. Okay, and you consider a simple object, which is the number of triangles, a number of triplets of people who are all friends with each other. And there's an easy computation. You can compute that the expected value of the number of triangles in this graph, you can exactly write it down. So there's n choose 3 is the total number of triangles, and each of them is actually a triangle in the graph with probability p cubed, and so on. So now the large deviation question is, what is the probability that there are k triangles where k is some number much bigger than this expected value? So what is the chance that there are many more triangles than what you'd expect? Okay, so that's a basic question that you can ask about the graph. And what does the graph look like if such a rare event happens? So if you observe many more triangles, you observe 3 people being all friends with each other many more times than you would expect just by chance, what does the graph look like? So this is an example of a nonlinear problem because the number of triangles is a nonlinear function of the adjacency matrix. The adjacency matrix of the graph is the matrix which has zeros or ones depending on whether there's an edge between I and j or not. And this is the entries are all independent. And this is a nonlinear function of this entry. So this is a very simple, basic nonlinear question, one of the simplest you can think of. However, the strange thing is that this was open. So this was completely open. People didn't know how to do this, this large deviation. So this thing about number of heads in n coin tosses, this was a basic linear question, and it is very old. People knew how to do this for a very long time. But this question, you go one step higher. You just take a random graph with all independent edges, and you look at the number of triangles. And what is the chance that there are many more triangles than you expect, or what does the graph look like if? So by many more, I mean maybe 2 times, or 1.5 times more triangles. So if it was just a little bit more, people understood that. Very small, infinitesimally more, people understood. But if it was a fraction more, there was no understanding of how to even approach this question. So this was done. So I, together with Raghu Varadan at NYU, we did this in 2011. And so this theory brought together things from various areas. So it's a bunch of large deviation techniques, and there were Samaridy's regularity lemma, and then there was the graph limit theory developed by Lofas and co-authors. So various things came together, which was pleasing. So here is an example, the kind of results. So I'll give you, in this slide, I'll give you a very counterintuitive sort of result that you get from this investigation. So recall this model. You have n individuals, any 2 are friends with probability p independently, and t be the number of triangles. Let et be the expected number of triangles. And so you would want to know what is the most likely structure of the graph if this rare event happens, that the number of triangles is a fraction more than the expected value. So there are various possibilities. One is that all the extra triangles are contained in a small subset of vertices which have high connectivity among themselves. So the graph can look like that. There's a small bunch of vertices which are highly connected. There's sort of a clique of people, so that they give all the more triangles. Or it can happen because there is an excess number of edges spread independently. It's just that there are many more friendships than you would expect, so just uniformly distributed. So what is it? What is the most likely scenario? So surprisingly, the theory implies that both scenarios can happen. Okay, so that was a surprise to us. So more precisely, it's the following. So I'll say it in words in the next slide, but just let me say it in math in this slide. There exists delta 1 and delta 2, 2 numbers. So that if this delta here is between delta 1 and 0 or bigger than delta 2, then conditional on this event, the graph just behaves like an heterogeneous graph. So it just behaves as if there were an extra number of friendships or edges spread out uniformly all over. Okay. On the other hand, if delta is between delta 1 and delta 2, then the conditional structure is different. So then there is a clustering. Okay. So that, So these, and I should say that then there was this very nice work of Lubetsky and Zhao afterwards, where they found these formulas for delta 1 and delta 2. So there's this symmetric and broken symmetry regime, and they found the exact boundaries between. So they had a phase diagram in the language of statistical mechanics. Okay. So in words, what this means is the following: that if the number of triangles exceeds the expected value by a little bit or by a lot, then the most likely scenario is that the excess number of edges spread uniformly. Okay, so you have this graph, you observe an excess number of triangles. If the excess number is a small fraction more or is a large fraction more, then you would expect the heterogeneous behavior. Then you would expect that all the edges are spread uniformly. Whereas if it belongs to middle range, then there is a clustering of edges. Then you can say that with high probability, there is a clustering of edges. And the exact nature of this is still not fully understood. So in the sense of this graph limit theory, which I don't have time to go into now. But it comes as a solution of a variational problem, and we cannot solve the problem, but we can show that there is a clustering. Okay, and the thing is, so this demonstrates the value of mathematics, because these results cannot be guessed, and I still don't know what's the intuition, that you get this sort of uniform behavior if you have a little more or you have a lot more, but somewhere in between you get a clustering. So we don't have any understanding of why this happens. It just comes out of the calculations. That now we have tools by which to calculate things, and these calculations can yield these results, which you cannot justify by other means. Any questions till now? Yes?
Can the clustering be described as a phase transition?
It is a phase transition. It is a phase transition. So I wasn't wanting to go into that. So it's in a statistical mechanics language. There is an order parameter, which is what is called a graphon in the graph limit theory, and this order parameter. So there is a variational problem whose solution can either be a constant function, which is a symmetric regime, or it can be a non-constant function, so it's a broken symmetry, region of broken symmetry. And there can be more than, so we identified these two phase transitions that happen. There can be more happening in between, and we still don't know whether it happens. Yes. There can be, we don't.
One of the things that, in the case where there's a cluster, it doesn't say there aren't other.
No, it doesn't, yeah, yes.
Do delta 1 and delta 2 depend on N and P, or are they just?
No, they depend on P. So they don't depend on N, because it's an asymptotic result. So this result P is fixed, but N is going to infinity. Okay, so they depend on P, delta 1 and delta 2. Yeah. So this was a very clever piece of work where they actually found this. We tried very hard. Raghu and I tried very hard to get this, but we couldn't.
Any example pictures?
What?
I mean, pictures of graphs representing the clusters.
No, so the thing is, there is a difficulty doing that, because you have to, okay, so this is another value of large deviations. You have to simulate conditional or rare event. Now the event is rare, right? So the chances are extremely small. So you may have to wait for many years before you get something by these simulations. But the thing is, rare events do happen. Hundreds of millions of people buy the lottery and somebody wins. So okay, so rare events do happen. Okay, so then there are some other applications. There are these exponential random graph models, which are widely used in the analysis of real social networks, and we can say things about those also. Now there is an incompleteness of this theory. So there's the large deviation theory for random graphs. It was fairly well developed in our paper and subsequent papers, but has one very serious shortcoming, which is that it applies only to dense graphs. So what does it mean? So a graph is called dense if most vertices are connected to a sizable fraction of other vertices. Okay? So for instance, in the heterogeneous graph where n is 10,000 and p is 0.3, so there are 10,000 people and any two are connected with chance 30%, then each person has approximately 3,000 other friends, okay? Which is an unrealistic scenario. So if you have 10,000 people in a real social network, even if the heterogeneous model is true, p would be like 0.01, 100 people, 100 friends. So the real networks are usually sparse. So this dense case we did just as a first step to understanding the thing. Now the problem is the main issue. So there is a deep graph theoretic issue here, which is that the graph theoretic tools that we used for this analysis, Samarity's lemma and the graph limit theory of Lovas and co-authors, they are useful only for the dense case. Okay. And this, for instance, developing a satisfactory version of Samarity's regularity lemma. So this is an open problem for 40 years. So, and I'll tell you why that is. So I'll tell you what's the underlying reason why this is challenging. So the main issue is the following: that the problem is to enumerate the number of graphs with a given set of properties. So for instance, you have to understand how many graphs are there with m edges and k vertices. Okay, this is the kind of thing that you have to understand. Now, for dense graphs, this approximate counting is possible with Samarity's lemma. So how is this? So I won't tell you, and I don't have time to tell you what this lemma is, but what it does is the following. it classifies the set of all dense graphs on n vertices into a bounded number of types. And the number of types depends on the desired accuracy of approximation. So you want to approximately count something, and you want approximation up to error epsilon. So depending on epsilon, you can classify the graphs into types. So it's sort of a compactness thing. The number of types will just depend on epsilon. And within each type, you can count using classical large deviation technique. So that's the combination of large deviations and similarity lemma that comes in. And the graph limit theory will allow you to take a limit to infinity, so to embed the whole thing into an infinite object. So the regularity lemma is inapplicable in the sparse setting. We do not know how to classify sparse graphs into types. So I'll tell you a little bit more on how this means. So what this means. So for instance, an excess number of triangles in a sparse graph can occur because there are extra edges that are distributed uniformly, or a small number of vertices that are highly interconnected, or a small number of vertices that are high connectivity to the rest. And these small things can happen in very tiny regions in sparse graphs. So in a dense graph, very tiny regions don't matter. So you can just forget about them. But in sparse graphs, even very tiny regions can give rise to serious anomalies. And this classification, what are all possible structures of sparse graphs? This is not yet captured by any tool that we have in graph theory. Okay, so we really don't understand this. Now, so we tried hard to get around this problem, and then so with Amit Dembo at Stanford, I have a paper which is the same title as the title of this talk, Nonlinear Large Deviations, which goes beyond this graph theoretic setting and bypasses the regularity lemma. So I look at it from this different viewpoint, going beyond the graph theoretic setting, and using this, so I'll tell you one outcome of this new theory is that there is this more recent work of Lubetsky and Zhao, where they show the following. You consider the Erdős-Srény graph GNP. You look at the probability that the number of triangles exceeds the expected value by a fraction delta. Now, delta is fixed, but here n is going to infinity, and p, instead of remaining fixed, is going to 0. But okay, there's this barrier, so the theory is still incomplete. But going to 0 slower than this, then you have this explicit formula of the probability. It's like e to the minus n squared p squared log 1 over p times a constant, which is the minimum of these two things. And then there is a follow-up paper, so I'll tell you about that. So this problem was open for a very long time, this upper tail problem. So there is a paper of Svante Jansson called the infamous upper tail, this upper tail problem for triangles. So initially, they didn't even know what are the right exponents on n and p. And then that was fixed. And then there was, this log factor was missing. And then, I was one of the people who fixed that. There's a log factor. But this constant dependence on delta was completely open. And now this is known because of this work, which uses this. And this, this thing comes because of some limitations of this theory, of the nonlinear large deviation theory. And this has been generalized by these 4 authors more recently, where they go beyond triangles, they go to other subgraph counts, and they can handle these objects. Okay, so here is a summary. So the main problem is that we do not yet understand the nature of sparse graphs. The thing is, we understand some sparse graph structures, but not all possible structures in totality. So the similarity lemma gives you a classification of all possible structures that a dense graph can have. So somehow it gives a complete classification of that, as a compactness theorem. So it tells you that it's a compact. Essentially, it's embeddable in a compact space, and you can identify the correct metric and so on. But we do not understand the sparse graphs. We don't know how to embed sparse graphs in a compact space and understand the structure by that method. The problem can be solved by if somebody can prove a suitable version of the regularity lemma for sparse graphs, but this would have many consequences, including various famous things of recent times, such as the Green-Tau theorem. But there is no hope for a solution as far as I know. So instead, what we did is circumvented the problem using these tools of nonlinear large deviations, which unfortunately I don't have the time to tell you what the main results are and what the things are. But anyway, they already have several breakthroughs. And the theory is still not complete. You saw that n to the minus 1 over 42, and that should go to n to the minus a half. So that needs improvement. And from the applied perspective, there's a gap between networks that appear in the real world versus networks whose large deviation properties can be theoretically analyzed. So there are many, many networks that appear in the real world, and you would want to understand what happens if something rare. So the main problem with rare event analysis is that it's hard to just do a simulation and, okay, you don't need to do math, you just do a simulation. Okay, you can wait forever. Simulation will never converge. So you cannot do a rare event analysis using simulations. You need to do the math. And we don't know how to do that. So that's a problem that needs to be bridged. Okay, thank you.
Thank you. I think we have time for some questions if people would like to ask. Yes, yes.
Does this apply to Facebook where everybody has 3,000 friends?
I'll get out of your way.
Yeah, well, no, it doesn't. So Facebook, first of all, the structure of Facebook, it's hard to do mathematical modeling, mainly because the data is not available. They wouldn't give us the data. So and I don't see any chance of that. So we.
The CEO is one of the, founder of this foundation, right? You can ask the CEO.
I don't know what's their interest. They have their own people who are trying to increase revenue, so that's mainly what.
There.
Are there examples that we're familiar with of dense graphs in real life?
So yeah.
Repeat the question for the mic, if nothing else. Yes.
Oh, sorry. Are there examples of dense graphs in real life that we might be familiar with?
Not so much. So, for instance, if you consider very small networks, like there is this example of a network of students at Caltech, which are like 700 some students, and in that it's not dense. But let's say if you consider all people who are friends of friends, okay, so then that it's an artificial example of a dense network. So people have some artificial examples of that. I've heard some other examples which come up from biology and so on, but not so much. So real-world graphs are almost always sparse.
Question there. There's a microphone.
If one writes down Semiraty's theorem in a quantitative way, the quantitative bounds are notoriously kind of weak. Does that have any effect on your theory?
So the thing is, that was the main reason why we needed to develop this new theory, because the quantitative bounds will let P go to infinity only as, you can use a weak regularity lemma, and even if you use the weak regularity lemma, the P can go to 0 only like some negative power of log n, and that's too slow. So we wanted to break that barrier and get to n to the minus something. And that's why we had to develop this new theory. And the graph theorists think that this theory may have some bearing on how to break the barriers that cannot be broken by Semiraty's lemma, but we aren't sure about that. So if you just use the quantitative regularity lemma, it won't give you anything like n to the minus some negative power of n. You won't get that.
All right. Thank you very much. That was a lovely presentation.